The water looks ordinary at first. A flat horizon, soft waves, a quiet blue surface that could belong to any ocean on Earth. But if you could peel time away instead of distance, if you could sink not just through depth but through eras, you would find that this sea was once ruled by giants. Not just one age, not one brief experiment, but a repeating pattern across hundreds of millions of years. Again and again, the oceans filled with creatures that were far too large for the world we know now. Why did the prehistoric oceans keep making monsters? Why were there so many titans below the surface? Armored fish the size of cars, reptiles longer than buses, turtles heavier than small cars, arthropods dwarfing anything similar today. And why does this pattern appear, vanish, and reappear like a heartbeat hidden inside the fossil record? To understand it, we have to dive, not just down into water, but down through layers of time, through sunlit shallows swarming with ancient reefs, through twilight zones lit with drifting armor and teeth, through midnight waters where predators moved like moving shadows, and finally into the abyssal trenches of pure speculation. Because science can explain pieces of this story, but not all of it. We begin in the sunlight zone, the bright upper skin of the prehistoric sea. Here, in warm, shallow shelves and inland seas that once covered continents, life exploded into complexity. Coral-like reefs, blooming microbial mats, forests of crinoids and brachiopods. This was the stage where the first serious arms races began. Early predators here did something strange. They didn't just get sharper teeth or faster fins. They started to get bigger. Long, conical-shelled cephalopods cruising over the seafloor, early-jawed fish wrapped in bone like moving fortresses, sprawling arthropods patrolling the bottom like armored tanks. Creatures that, compared to their neighbors, were simply oversized. In the bright waters, food was abundant. Sunlight powered algae. Algae fed small grazers fed hunters. The more energy pumped into this system, the more biomass it could support, and the easier it became for at least a few lineages to push size to extremes. Large bodies offered simple advantages. You were harder to swallow, stronger in a grapple, and able to take larger prey in single, decisive strikes. But this isn't enough to explain what we see, because it didn't just happen once. Wave after wave of very different creatures, cephalopods, arthropods, armored fish, marine reptiles, each in different eras, each in different climates, found their way to extraordinary size, almost as if the ocean kept reusing the same trick with completely new casts. Now the light begins to thin. We sink past the crowded reefs and into the pale blue twilight zone, where color drains from the water and shapes start to blur. Here, the giants change. They are no longer just hunters of the reef edge. They are rulers of open water, vast inland seas and continental margins stretching to the horizon. Imagine a sprawling, shallow sea where the land you know is gone, buried under warm water. In this world, enormous predators patrol the mid-water column. Some wore plates of bone as if carved from stone. Others bore long, bladed jaws capable of biting through armor like paper. They did not tiptoe around the food chain. They sat on top of it, feeding on anything that dared to grow large enough to be worth the effort. Here, the arms race intensified. As prey developed thicker armor, predators evolved more powerful jaws. As jaws strengthened, prey fortified their bodies even more. This feedback loop does something interesting. It doesn't simply make animals tougher, it pushes them toward larger sizes, because large frames support thicker armor, stronger muscles, and bigger biting surfaces. But again, there's a problem. This pattern repeats across different eras with different animals, but not everywhere and not always. Why did some seas become arenas of giants while others did not? If it was just about food, armor, or simple predation, we might expect a smoother gradient through time. What we see instead are spikes, periods where giants crowd the top of the web, followed by collapses where those giants vanish. We keep sinking. The blue fades to a heavy indigo, then into deep, oppressive shadow. We're entering the midnight zone of prehistory, not just in depth, but in uncertainty. Here, some of the strangest giants of all stalked the water. Now picture reptilian superpredators sweeping through the dark, their bodies powered by lungs, not gills. They carved through schools of fish, swallowed marine reptiles, hunted anything that moved. They were not slow, clumsy beasts. They were built for pursuit, for killing, for owning the water column. Around them, enormous fish, massive turtles, and huge invertebrates shared a world scaled far beyond today's average marine life. Several things were happening at once. Sea levels were high, creating immense shallow seas ringing the continents. Warm temperatures extended productive waters across huge areas, feeding dense food webs. With energy flowing and prey growing larger, top predators had evolutionary room to expand their bodies to match. But simply saying there was more food doesn't explain why so many top predators converged on such extreme sizes, or why this happened in multiple unrelated lineages. Reptiles, fish, and vertebrates, they took different evolutionary paths, yet all arrived at the same outcome: towering forms that dominated entire ecosystems. The ocean allows large bodies, that much is clear. But something kept pushing those bodies toward the upper limit of what bone and muscle could support. And still, every one of those lineages eventually hit a wall. Environmental shifts, collapsing food webs, climate swings, catastrophic impacts, all acted like scythes cutting down the giants. What once seemed invincible shrank, disappeared, or was replaced. Gigantism in the oceans was not a straight line. It was a boom and crash cycle, repeated again and again. Now the water around us is almost completely black. We're deep in the abyss, where pressure builds and light never reaches. Out here, modern giants drift in silence. Colossal squids, massive whales, sprawling jellyfish like living parachutes. But in the prehistoric world, the abyssal story is harder to read. Fossils are rare down here. Bones collapse, soft bodies vanish. Yet even with limited evidence, we know this: size did not belong only to the surface. Large-bodied animals likely roamed the deep too. Ancient relatives of modern deep-sea forms stretched to scales that would seem impossible in today's sparse abyss. In the deep, the rules of survival are different. Cold water slows metabolism. High pressure allows flexible bodies to grow large without collapsing, while low temperatures and slow life histories can favor creatures that live long and invest in massive, energy-efficient bodies. In such a world, being huge can mean outlasting famine, gliding long distances between rare feeding grounds, and dominating scarce resources when they appear. But here, the mystery only sharpens. Prehistoric oceans were often warmer, not colder, yet the fossil record still points toward repeated bouts of gigantism both near the surface and in deeper waters. Different temperature regimes, different food distributions, yet the same outcome: giants. Why do such different environmental conditions keep converging on similar extremes of size? We can name partial causes: buoyancy, predation, productivity, oxygen pulses, ecological release after mass extinctions. Each explains a slice of the pattern. None of them fully explain why giant after giant appears, flourishes, and then disappears, only to be followed by another, completely unrelated titan a few tens of millions of years later. We sink one layer deeper into the trenches. This isn't just the deepest water, it's the deepest question. Down here, there are no clear fossils, no intact skeletons, just scattered bones and broken traces. We are mostly left with theory. One idea suggests that gigantism is simply what happens when evolution runs out of easy tricks. Once speed, stealth, armor, and venom have all been tried, scaling up becomes the simplest way to dominate. You become harder to kill, harder to ignore, harder to starve. In a world where everything is competing, being bigger is a brute force solution. But if this were the whole story, we might expect giants everywhere, in every era, in every ocean. Instead, we see clusters, bands of time where giants are common, followed by long stretches where the seas are quieter, dominated by smaller, more modest life. It's as if the ocean occasionally opens a window where being enormous works astonishingly well, and then slams it shut. Maybe the trigger is mass extinction. When catastrophic events wipe the slate clean, ecosystems reset. In the aftermath, with food webs rebuilding and niches wide open, there might be room, not just for small survivors, but for lineages that can rapidly scale up into vacant roles, becoming oversized hunters, grazers, or scavengers. In those moments, ruling the water may belong to the biggest bodies evolution can construct before the environment shifts again. Or perhaps our record is distorted. Fossils are biased toward creatures with hard shells, heavy bones, and thick armor, precisely the kinds of structures found in giants. Smaller, more delicate animals vanish into the sediment without a trace. Maybe prehistoric oceans were not especially filled with giants. Maybe giants are simply what we see most clearly through the fog of deep time. But that explanation has its own cracks. The pattern of gigantism isn't random noise. It appears in independent lineages across separate oceans and geological periods. It involves predators and prey, reptiles and fish, arthropods and cephalopods. If it were just a trick of preservation, we would expect more chaos in the pattern, not repeating peaks of enormous size woven through the history of the sea. Look around, even now. The largest animal that has ever lived on Earth is not a dinosaur from the past, but a whale alive in the modern ocean. Colossal squids still stretch beyond the length of small boats. Leatherback turtles still cross oceans with bodies heavier than most land predators. Marine gigantism did not vanish, it changed shape. Today, warm-blooded hunters dominate many marine food webs, using high metabolism, blubber, and efficient lungs to thrive in cold, deep waters. Their gigantism follows different rules. They are fueled by dense swarms of small prey, krill, fish, and cephalopods, rather than by armored giants the size of cars. The blueprint has shifted, but the theme remains. The ocean keeps finding ways to make life huge. So why did prehistoric oceans feel different? Why were they filled with such a diversity of giants built from bone, cartilage, chitin, and shell, creatures that look almost theatrical in their excess? Why did some eras swarm with massive predators and colossal grazers, while others retreated into a world of smaller, subtler forms? Perhaps gigantism is not a single phenomenon, but a repeating answer to different questions. In some eras, it solved the problem of predation. In others, it solved the problem of resource competition. In still others, it may have been a response to climate, currents, chemistry, or events we have barely begun to reconstruct. Many causes, one visible outcome, bodies pushed to the limit. And yet, after all the equations and models, something remains unresolved. The fossil record shows us that giants appeared repeatedly, in different oceans, under different skies, with different rules. It shows us that the sea is capable of building size beyond anything stable on land, again and again. But it does not tell us why the ocean seems to love extremity. So we are left with this. The prehistoric oceans were not merely larger versions of today's seas. They were worlds that flirted with biological extremes, that allowed evolution to test just how big a predator could be, how thick armor could grow, how far a turtle could stretch its shell, how long a cephalopod could become before its own body became a burden. Sometimes those giants thrived for tens of millions of years. Sometimes they disappeared almost as soon as they arrived. We can say that buoyancy favored them, that energy flows fed them, that arms races sculpted them. We can trace their bones, reconstruct their jaws, measure the scars they left on the shells and skeletons of their prey. But we still cannot answer with certainty the simplest question. Why did the prehistoric oceans, again and again, choose to fill themselves with giants? Maybe it is a feature of evolution itself, that whenever life is given space, energy, and time, it will eventually test the upper limits of what a body can be. Maybe the giants of the past were not anomalies at all, but an inevitable expression of biology in a generous world. Or maybe we are missing something. Some deep systemic rule about how oceans organize themselves over millions of years. A rule that shapes not just who survives, but how large they are allowed to become before the world changes and the experiment ends. Until we can fold time like water and watch those seas directly, we are trapped with fragments. A tooth here, a shell there, a bone the size of a person's arm. Evidence that once, long before our species ever saw the ocean, the water was ruled by creatures that dwarfed anything we have ever known. Why did the prehistoric oceans have so many giants? For now, the truest answer is the one the fossils refuse to give us. They show us that it happened. They whisper hints about how. But the deeper question, why this much, this often, in this way, still drifts somewhere in the dark water between what we can model and what the ancient sea still refuses to reveal.